The Quantum Revolution, a deep strategic analysis of humanity's next technological leap. Introduction, understanding the gravity of the quantum moment. Let me help you understand why quantum computing represents not just another technological advancement, but a fundamental reimagining of computation itself. Imagine for a moment that all of human history's computational power, from the ancient abacus to today's most powerful supercomputers, has been like trying to explore the ocean by walking along the beach. Quantum computing is the moment we finally learn to swim, and then to dive into depths we never imagined possible. The document you've shared captures something profound about our current historical moment. We stand at a threshold where the nations and organizations that master quantum mechanics at the computational level will essentially rewrite the rules of power, security, and human capability for the next century. This isn't hyperbole, it's the sober assessment of physicists, strategists, and technologists worldwide who understand what's truly at stake. The physics that changes everything, understanding qubits at a fundamental level. To truly grasp the quantum revolution, we need to start with the qubit itself, and I want to help you understand this in a way that goes beyond superficial analogies. A classical bit is deterministic. It exists in a definite state of either 0 or 1, like a light switch that's definitively on or off. This binary certainty has been the foundation of all digital technology since Turing and von Neumann laid the groundwork for modern computing. A qubit, however, exists in what physicists call a superposition state. Think of it this way. If a classical bit is like a coin that has landed and shows either heads or tails, a qubit is like a coin spinning in the air, simultaneously embodying both possibilities until the moment of measurement. But here's where the analogy breaks down in a fascinating way. The qubit isn't simply undecided or random. It exists in a precise mathematical superposition described by complex probability amplitudes that can interfere with each other constructively or destructively, much like waves in water. This superposition property alone would be revolutionary, but quantum mechanics offers something even more: entanglement. When qubits become entangled, they form a unified quantum system where the state of one qubit instantaneously correlates with the state of another, regardless of the distance between them. Einstein famously called this spooky action at a distance because it seemed to violate the principle that nothing travels faster than light. Yet experiments have consistently confirmed that entanglement is real, and it's this phenomenon that gives quantum computers their exponential computational advantage. Let me illustrate the power with a concrete example. A classical computer trying to analyze all possible configurations of a protein with 300 amino acids would need to examine roughly 10 circumflex 390 possibilities in numbers so large that there aren't enough atoms in the observable universe to represent it. Even if every atom in the universe was a supercomputer working since the Big Bang, they couldn't complete this calculation. A quantum computer with sufficient qubits could explore all these possibilities simultaneously through superposition, finding the optimal configuration in hours or days rather than eons. The global strategic landscape, understanding the new great game. The quantum race represents a new form of geopolitical competition that combines elements of the space race, the nuclear arms race, and the current AI competition, but with unique characteristics that make it particularly consequential. Unlike nuclear weapons, which primarily serve as deterrents, quantum computers are tools of active power projection in the information age. Unlike classical computing advances, which have been relatively incremental, quantum computing promises discontinuous leaps in capability. China's quantum program deserves particular attention because it represents a coordinated national strategy that integrates civilian research, military applications, and industrial development. When China launched the ambitious quantum satellite and successfully demonstrated quantum key distribution over intercontinental distances, they weren't just achieving a scientific milestone, they were demonstrating the ability to create unhackable communication channels that could fundamentally alter the balance of intelligence and military power. The Chinese government's construction of a dedicated quantum research city in Hefei, with thousands of researchers and billions in funding, shows a level of commitment that treats quantum computing as a civilizational priority rather than just another research area. The United States, despite its technological prowess through companies like IBM, Google, and Microsoft, faces a coordination challenge. The American approach relies heavily on private sector innovation, which excels at creating breakthrough technologies, but may struggle with the patient, long-term investment that quantum computing requires. The recent CHIPS and Science Act represents an attempt to bridge this gap, but whether it's sufficient remains an open question. The classified quantum programs within the Department of Defense and intelligence agencies add another layer of complexity. We simply don't know the full extent of American quantum capability. Europe's approach offers an interesting alternative model. Rather than competing directly with the US and China in raw computational power, European researchers are focusing on quantum technologies that could provide nearer-term practical benefits. quantum sensors for medical imaging, quantum cryptography for financial systems, and quantum simulators for materials science. This specialization strategy might allow Europe to capture significant value from quantum technologies without winning the race to the most powerful quantum computer. What's particularly fascinating is watching smaller nations like Singapore, Canada, and the Netherlands punch above their weight in quantum research. These countries have identified specific niches where they can achieve global leadership, proving that the quantum revolution isn't solely the domain of superpowers. Revolutionary applications that will transform human civilization. Let me walk you through the applications of quantum computing in a way that reveals their true transformative potential, starting with cryptography and security. Modern encryption relies on mathematical problems that are easy to verify but computationally infeasible to solve. The RSA encryption protecting your bank transactions, for instance, depends on the difficulty of factoring large numbers into their prime components. A number with 2048 bits would take classical computers billions of years to factor, but Shor's algorithm running on a quantum computer with perhaps 4,000 logical qubits could break it in hours. This isn't just about breaking codes, it fundamentally undermines the entire infrastructure of digital security built over the past 50 years. Every encrypted message, every secure transaction, every protected database becomes potentially vulnerable. Intelligence agencies are already conducting harvest now, decrypt later operations, storing encrypted communications with the expectation that quantum computers will eventually make them readable. This creates a peculiar temporal vulnerability where secrets protected today may be exposed retroactively, and the thing offers quantum key distribution uses the fundamental properties of quantum mechanics to create provably secure communication channels. Any attempt to intercept or measure the quantum states being transmitted necessarily disturbs them, alerting the communicating parties to the presence of an eavesdropper. This isn't just very secure or practically secure, it's secured by the laws of physics themselves. In drug discovery and molecular modeling, quantum computers address a fundamental limitation of classical computation. Molecules are quantum mechanical systems, and simulating them classically requires exponentially growing resources as the system size increases. A quantum computer, operating on the same quantum mechanical principles as the molecules themselves, can simulate them naturally and efficiently. This means we could design drugs that precisely target specific proteins, develop catalysts that make industrial processes vastly more efficient, or create materials with properties we can barely imagine today. Consider the implications for addressing climate change. Quantum computers could design new catalysts for carbon capture that work at room temperature and atmospheric pressure, making it economically viable to pull CO2 directly from the air. They could optimize power grids in real time to minimize waste, or design new battery chemistries that store energy with densities approaching that of fossil fuels. These aren't incremental improvements, they're potential paradigm shifts in how we interact with energy and the environment. The deep technical challenges, why quantum computing is so difficult. Building a quantum computer isn't just technically challenging, it requires us to maintain quantum coherence in a world that seems designed to destroy it. Let me explain the profound difficulty of this challenge. Quantum states are incredibly fragile. A single photon of stray light, a minute vibration, even the gravitational pull of a person walking nearby can cause decoherence, the collapse of the delicate quantum superposition into a classical state. Current quantum computers operate at temperatures near absolute zero, about 0.015 Kelvin, in IBM's systems, which is colder than outer space. They achieve this using dilution refrigerators that are marvels of engineering in themselves, using rare helium-3 isotopes and creating some of the coldest environments in the known universe. The qubits themselves are often superconducting circuits made from aluminum and Josephson junctions, operating in a regime where quantum effects dominate over thermal fluctuations. But even with this extreme isolation, current qubits are noisy. They have error rates around 0.1% to 1% per operation, which might seem small but quickly compounds. Imagine trying to perform a calculation requiring 1 million operations, even with 99.9% accuracy per operation. Your final answer would be worthless. This is why quantum error correction is perhaps the most important challenge in the field. The solution involves using many physical qubits to encode a single logical qubit, with sophisticated error correction codes that can detect and correct errors without destroying the quantum information. The scaling challenge adds another layer of complexity. It's not enough to have stable qubits, you need to be able to control them precisely and have them interact in controlled ways. In a system with 1,000 qubits, you need to be able to address each qubit individually, implement 2 qubit gates between arbitrary pairs, and read out the results, all while maintaining coherence. The control electronics alone for such a system would traditionally require a room full of equipment for each qubit. Companies are now developing specialized control chips that can operate at cryogenic temperatures, sitting right next to the qubits themselves. Chapter 5, a strategic roadmap for quantum leadership. Building quantum capability isn't just about purchasing technology or hiring experts. It requires a coordinated national strategy that aligns education, research, industry, and government policy. Let me outline a comprehensive approach that goes beyond superficial measures to create genuine quantum competitiveness. The foundation must be human capital development, but this needs to be understood broadly. We're not just talking about training quantum physicists, though that's certainly important. We need quantum engineers who can build and maintain these complex systems, quantum programmers who can develop algorithms and applications, quantum entrepreneurs who can identify and develop commercial opportunities, and perhaps most importantly, quantum literate leaders who can make informed, strategic decisions about this technology. Consider establishing a national quantum academy that operates differently from traditions on experience using real quantum hardware. Industry partnerships that ensure relevance to practical applications, and international exchange programs that prevent insular thinking. The curriculum should be dynamic, updated quarterly based on the latest developments in the field, because quantum computing is advancing so rapidly that traditional academic timelines are too slow. Infrastructure development requires thinking beyond just purchasing quantum computers. You need to build an ecosystem that includes specialized fabrication facilities for quantum devices, because relying entirely on foreign-made components creates strategic vulnerabilities. You need ultra-low vibration laboratories with sophisticated electromagnetic shielding. You need reliable supplies of liquid helium and specialized isotopes. You need high bandwidth, secure networks for distributed quantum computing. Each of these elements requires years of planning and development. The innovation ecosystem is equally critical. Quantum startups need different support than typical tech companies. They require patient capital willing to wait a decade or more for returns, access to expensive specialized equipment that no startup could afford alone, and connections to academic researchers at the cutting edge of the science. Consider creating quantum innovation hubs that provide shared facilities, equipment, and expertise, similar to how biotech incubators provide shared wet labs. Chapter 6. Future scenarios and their strategic implications. Let me paint 3 detailed scenarios for how the quantum future might unfold, each with radically different implications for global power structures and human society. In the quantum supremacy scenario, imagine that by 2035, one nation or a tight alliance achieves a decisive quantum advantage, perhaps a million-qubit fault-tolerant quantum computer, while others are still struggling with thousands of noisy qubits. This wouldn't just be a technological edge. It would be a capability gap similar to one military having aircraft while others are still using cavalry. The quantum supreme power could break any encryption, design materials and drugs beyond others' capability, optimize their economy and military logistics with unprecedented efficiency, and potentially develop new weapons based on quantum principles we haven't yet imagined. Other nations would face a stark choice: accept subordination or attempt to create isolated quantum-proof systems that would necessarily be less efficient and cut off from the global digital economy. The quantum multipolarity scenario envisions several powers achieving significant quantum capabilities around the same time, creating a complex balance of power. We might see quantum spheres of influence where different regions use incompatible quantum technologies and standards. There would be quantum arms control treaties attempting to limit the most dangerous applications while allowing beneficial uses. Smaller nations would need to choose quantum alliances carefully, as new might be impossible when your digital infrastructure needs quantum protection. This scenario might be more stable than unipolarity, but would involve constant technological competition and the risk of quantum arms races. The quantum democracy scenario imagines a breakthrough that makes quantum computing accessible to everyone, perhaps room temperature quantum computers using common materials, or a revolutionary new approach that sidesteps current technical challenges. In this world, individual privacy could be absolute through personal quantum encryption. Small groups could tackle problems previously requiring government-scale resources. Traditional power structures based on information asymmetry would crumble. This scenario might be the most beneficial for humanity as a whole, but also the most disruptive to existing institutions. Chapter 7. Immediate actions and long-term strategy. The window for entering the quantum race meaningfully is narrowing rapidly. Let me provide specific, actionable recommendations that recognize both the urgency and the complexity of this challenge. For national leaders, the first step is creating institutional focus. Establish a National Quantum Initiative Office with real authority and budget control, reporting directly to the highest levels of government. This isn't just another bureaucracy. It needs to be a dynamic organization capable of making rapid decisions and coordinating across traditionally siloed departments. Give it the authority to override normal procurement procedures when necessary, because the typical government acquisition process is too slow for this rapidly evolving field. The investment strategy needs to be bold but intelligent. Rather than trying to compete with the billions being spent by major powers, identify specific niches where you can achieve leadership. Maybe it's quantum sensors for oil exploration if you're an energy economy, or quantum computing for Islamic finance if you're a Muslim majority nation, or quantum technologies for tropical agriculture if you're an equatorial country. The key is finding areas where your unique characteristics or existing expertise provide an advantage. For businesses, the imperative is to start experimenting now, even if quantum advantage seems years away. The learning curve for quantum computing is steep, and companies that wait until the technology is mature will find themselves hopelessly behind. Begin by identifying problems in your business that are computationally constrained optimization problems, molecular simulations, machine learning tasks that take too long. Partner with quantum cloud providers to experiment with solving these problems on current quantum hardware, not because today's machines will provide advantage, but because you need to develop the expertise for when they do. Educational institutions need to fundamentally reimagine their approach to quantum education. This isn't just adding a quantum computing course to the physics department. Quantum information science sits at the intersection of physics, computer science, mathematics, and engineering. Create interdisciplinary programs that reflect this reality. More importantly, introduce quantum concepts earlier in education. High school students can understand superposition and entanglement if taught properly, and early exposure will create the quantum native generation we desperately need. Conclusion: the quantum imperative. We stand at one of those rare historical inflection points where the decisions made in the next few years will reverberate for generations. The quantum revolution isn't a distant possibility, it's an ongoing transformation that's accelerating rapidly. Every month brings new breakthroughs, new players, and new applications we hadn't imagined. The nations, organizations, and individuals who recognize this moment and act decisively will shape the next era of human civilization. Those who hesitate, who treat this as just another technology trend to monitor, will find themselves progressively marginalized in a world where quantum capability determines economic competitiveness, national security, and scientific advancement. But beyond the competitive dynamics, the quantum revolution offers something profound: the ability to understand and manipulate nature at its most fundamental level. We're not just building faster computers, we're learning to harness the deepest principles of reality for human purposes. The medical breakthroughs, the materials discoveries, the scientific insights that quantum computing will enable could usher in an era of abundance and capability that makes today's technology seem primitive in comparison. The choice before us isn't whether to engage with quantum computing. That question has been answered by the billions being invested and the thousands of researchers dedicating their careers to this field. The only choice is whether to be an active participant in shaping this quantum future, or a passive recipient of technologies and standards determined by others. History teaches us that technological revolutions wait for no one. The Industrial Revolution transformed agricultural societies into industrial powers in a single generation. The Information Revolution reshaped the global economy in just decades. The Quantum Revolution will likely move even faster, and its impacts will be even more profound. The time for half measures and committee studies has passed. The quantum age demands bold vision, decisive action, and the courage to invest in a future that's still taking shape. Those who rise to this challenge won't just survive the quantum transformation, they'll help define what it means to be human in an age where the boundary between the possible and impossible is constantly being redrawn. The quantum future is not a destination we're approaching, it's a reality we're already entering. The only question that remains is, what role will you play in shaping it? My own forecast is clear. The moment the first practical quantum computer is launched will mark the true beginning of AGI, artificial general intelligence. From that point forward, humanity will have started its hour of departure. A philosophical and existential transition where the limits of human-driven intelligence give way to an era of machine-driven cognition rooted in quantum reality.